Howdy, welcome to Math 153 Elementary Statistics. I am Lance Curtis, and this is the lecture for sections 8.1 and 8.2. As you can see here in chapter 8, we're going to be discussing these 5 sections, starting with a review and preview. So let's hype into it. Now, earlier in the course we discussed what's called descriptive statistics. So we were using summary statistics like mean and standard deviation. We're also using graphs, different ways in which we could characterize a data set. Then in chapter 7, we began what's called inferential statistics, which basically comprises 2 main activities. The first is to use sample data to estimate a population parameter. And this is what we did in chapter 7 with constructing confidence intervals. Now, in chapter 8, we're going to talk about testing a hypothesis or claim about a population parameter. This is the other main activity of inferential statistics. So, whereas previously we looked at confidence intervals in chapter 7, now we're going to look at hypothesis testing in chapter 8. What we want to do when we're conducting a hypothesis test is we're testing claims that are being made about population parameters such as proportion, mean, or standard deviation. So an example from the field of genetics would be that this institute claims that its XORT method allows couples to increase the probability of having a baby girl. An example from the world of business. A newspaper cites a pricegrabber.com survey of 1,631 subjects and claims that a majority have heard of Kindle as an e-book reader. An example from the world of health sciences. It's often claimed that the mean body temperature is 98.6 degrees. We can test this claim using a sample of 106 body temperatures with a mean of 98.2. So there's different ways that we could apply hypothesis testing, and this is just a very small sampling of all that we could do with hypothesis testing, but it's sufficient to communicate the point that there's a claim that's being made, and the hypothesis test is what we use in statistics to test the claim that's being made. So, like most things that involved using data, you want to know not just the actual end result, but you want to know about what you're putting in to get the result. It's just like most things. You put garbage in, you get garbage out. So you always want to make sure that you consider the context of your data. What does your data represent? Where does your data come from? How did you get the data? The sampling method that you use to obtain the data. All of these things are very important because if your data is missing some valuable data points or the data values are just off somehow because of the way that you sampled or because of the way that you're collecting your data, then that's going to affect the applicability of the conclusions you make from your hypothesis testing. So you always want to make sure that you're good with the data side because that's going to shore up the conclusions that you make on the back end. Now that we have that cleared away, let's jump into learning some of the basics of hypothesis testing here in section 8.2. And then in the following sections, we'll actually apply these basic methodologies to testing claims about population parameters, the proportion, the mean, and the standard deviation or variance. So to start off with in this section where we're talking about the basics of hypothesis testing, we want to first look at the individual components of a hypothesis test. And then we want to know and understand certain elements related to the hypothesis test. For example, we want to know how to identify the null hypothesis and the alternative hypothesis with a given claim. And we want to know how to express them symbolically. Math is all about symbols, so of course we want to know how do we represent these hypotheses symbolically. We want to know also how to calculate the value of the test statistic. The test statistic is what we're going to use to determine whether or not we quote-unquote pass the test. We also want to know how to choose the sampling distribution that is relevant. So just as we saw when we were conducting and constructing confidence intervals, we had to make sure we were choosing the right distribution. Well, we're going to see that same need for that concept come up again here in Chapter 8 with hypothesis testing. We also want to know how to identify the p-value or the critical value. We don't really need both, it's one or the other. I find it helpful to know both, as I'll explain when we get to that point in the lecture. But we do need to know how to do one or the other. And then we need to know how to state the conclusion that we make about a claim in simple and non-technical terms. Many of the people that need to know the results of the hypothesis test are not versed in statistics. And so they're not going to understand the statistical terminology if you state the conclusion in those terms. So you have to be able to communicate with people so that they can take the information the hypothesis test is presenting and present it in a way that they can act on it appropriately. So to start off with, when we talk about hypothesis testing, we first need to understand what a hypothesis is. And in terms of hypothesis testing, a hypothesis is nothing more than a claim or statement about a property of a population, so some parameter. So we're making a claim about a population mean, or a population proportion, or a population standard deviation, some parameter about the population. We're making a claim about it. That's the hypothesis. The hypothesis test is then the procedure that we use to test the claim about that property of the population. Now, in inferential statistics, we're only going to consider two types of hypotheses. So the first is what's called the null hypothesis, and the second is the alternative hypothesis. So every hypothesis test that we conduct will contain both a null hypothesis and an alternative hypothesis, as you'll see here shortly. Let's talk about each one of these in turn, starting with the null hypothesis. The null hypothesis is nothing more than a statement that the value of a population parameter is equal to some claimed value. So the claim that we're testing makes some assertion about a parameter and its association, its relationship to a certain value. Okay? The null hypothesis is basically saying that that population parameter that we're testing is equal to that claimed value. We're going to denote the null hypothesis with this symbol that you see here on the screen. It's a capital letter H with a subscript 0. This symbol is pronounced H sub 0, or in other quarters, it's pronounced H naught. I'm more comfortable with H naught, so you're just going to hear me call it H naught. But just understand, some people call it H sub 0. So either way, it's talking about the same thing. We can test H naught directly in the sense that we assume it to be true, and we reach one of two conclusions. The first conclusion that we could reach is that we reject the null hypothesis, which means that we accept the alternative. The other conclusion we could reach is that we fail to reject the null hypothesis, which also means we fail to accept the alternative. Notice how the terminology is very specific here, and we'll get to the reasoning for this later in the lecture. There's no accepting the null hypothesis. It's either reject or fail to reject. Again, we'll go into the reasoning later. But right now, you just need to understand that there's only these two possibilities, reject or fail to reject. So, by definition, okay, when you're talking about the null hypothesis, okay, remember the definition of null hypothesis is a statement that says the value of a population parameter, whatever it is that we're testing, is equal to some claimed value. So when we express the null hypothesis symbolically, we're going to use an equal sign almost exclusively. There are some very, very rare instances where you would use an inequality such as less than or equal to or greater than or equal to, but even these have some element of equality with them. For the homework problems that you're going to be doing, it's exclusively equals to, okay? Because that's the definition of null hypothesis, that the population parameter is equal to some claimed value. So by definition, when we express this symbolically, we're going to say that the population parameter we're testing is equal to whatever value is claimed. Now, the alternative hypothesis is simply the statement that the population parameter has a value that's different from what's claimed in the null hypothesis. So whereas the null hypothesis will claim that the population parameter is equal to a claimed value, the alternative hypothesis will say that the population parameter we're testing is not equal to that claimed value, or that it's less than that claimed value, or greater than that claimed value. Could be any one of those three. And which of those three will relate to more of how we do the test and the results that we gain from it. In all cases, though, we're going to denote the alternative hypothesis with one of two symbols, H sub 1 or H sub A. They're both equally common. I've seen both of them, there's one just as much as the other. So it's not like one's more common than the other, at least not in my experience. Your author uses H1, so in illustrating problems, I go with that one. But sometimes, I slip up and just put in the HA. Understand, whichever one you're seeing, they're the same thing. We're talking about the alternative hypothesis. Again, because the alternative hypothesis is defined as differing from the null hypothesis, which is defined as claiming that the population parameter we're testing is equal to some claimed value, then we're going to use a less than sign, a greater than sign, or a not equal to sign when symbolically representing the alternative hypothesis. One thing to keep in mind when you're forming your hypotheses for your test is that if you want to support a claim with your hypothesis test, then you need to state the claim in a way that it becomes the alternative hypothesis. In many instances, we can write the alternative hypothesis by looking at the claim and reflecting that claim into the alternative hypothesis. Here's an example that we're going to be looking at to illustrate the different parts of hypothesis testing. It's an example taken from gender selection. So that first example that we looked at earlier from genetics, if we assume that there's 100 babies born to 100 couples, so each couple has one child, and of those births, of 100 births, we've got 58 girls, okay? So then the question becomes, what are the null and alternative hypotheses that test the claim with the XORT method, the proportion of girls is greater than the 50% that occur without any treatment? So there's a claim that this methodology, if you apply this method, it's going to increase the likelihood that you'll have a baby girl instead of a baby boy. So what we want to do is we want to run a hypothesis test on that claim. And here's our sample. We've got 100 babies in the sample, and 58 of them are girls. Okay? So right away, we're looking at a proportion. That's the parameter of the population that we're trying to test. It's a proportion. Because there's nothing in here that talks about the mean or the standard deviation. It's strictly proportion. 58 out of 100. So that's what we're testing. The null hypothesis, then, we can write in this manner. P equals 50%. The P, again, is the proportion. That's the population proportion symbol equals. Okay, notice that the null hypothesis, by definition, will almost always take that equal sign. So just go ahead and write out equals when you're writing the null hypothesis. The 50% comes directly from the claim. So we're claiming that the proportion of girls with this method is greater than 50%. So then that's the claimed value that the null hypothesis is going to say the population parameter is equal to. Now that we've written our null hypothesis, we're ready to write our alternative hypothesis. And here it is. Population proportion is greater than 50%. Why greater than? Because that comes directly from the claim that's made in the problem statement. Here's the claim. The proportion of girls is greater than 50%. So then that means P is greater than 0.50. There's our alternative hypothesis. It's very common for the claim to be reflected in the alternative hypothesis, whereas the null hypothesis is almost exclusively your population parameter equals the claimed value. Now that we've got the hypotheses written, we need to look at the significance level. The significance level is similar to what we were looking at with the level of confidence with our confidence intervals. Okay? We represent the significance level as the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. In other words, this is a probability that we're going to commit what's called a type 1 error, where we reject the null hypothesis when it is true. We'll talk more about type 1 error later in the lecture. For right now, though, we just need to understand the significance level is denoted with the lowercase Greek letter alpha. This is the same alpha that we've seen previously in Chapter 7 when we were working with confidence intervals. So there's nothing different about this. This alpha is the area of the critical region. That's what we're calling significance level. Now, if you're thinking about what you're doing and not just punching buttons on software, then you're going to take into consideration the seriousness of committing a type 1 error, because that's going to influence the significance level that you're going to want to select for your hypothesis test. The reason why I say if you're thinking about what you're doing is because a lot of people, they just grab a significance level that they've always used, and a very popular one is 5%. In fact, 5% is the most popular one that's typically chosen. There's nothing really magical about 5%, though. It's simply one that just is chosen again and again, and it's nothing more than a convention. That 5% does play into the, as we saw with confidence intervals, okay, the width of your confidence interval is going to be determined by the significance level that you choose. So if you want a tighter interval, you want to choose a lower alpha level. Well, likewise, when we're talking about hypothesis testing, if the seriousness of committing a type 1 error is very egregious, then you want to select an alpha that's as small as you can get away with. So in those situations, it may behoove you to choose an alpha of, say, 1% or 1/10%. Understand that there are other factors that come out of this from a smaller alpha selection, but you want to be thinking about what you're doing and not just pushing buttons in software. For the most part, there are many instances in which a 5% significance level is just fine. But you always want to be trying to think about what it is you're doing in the event that you run into a situation where it makes sense to choose a lower alpha level. Again, common choices, 10%, 5%, 1%. We've seen these before. These are critical values that keep popping back up. We saw that with the confidence levels and the confidence intervals. We're going to see that again here with significance levels in hypothesis testing. Once we've selected our significance level, the next step is to calculate our test statistic. The test statistic is what we're going to use to make the decision about the null hypothesis. Remember, there are two conclusions we can make. We can either reject or fail to reject the null hypothesis. To do that, we need to calculate a test statistic. Here you see in the table on your screen a table of the different test statistics depending upon what parameter you're choosing. So notice that these test statistics are very similar to the test statistics that we saw earlier in Chapter 7 about confidence intervals. So not a whole lot new there. Also notice that we have two different test statistics for the mean. There's one test statistic for proportions. It's based on the normal distribution, so you're calculating a z-score according to the formula you see there. And standard deviation, again our old friend, the chi-square distribution, where you're seeing similar test statistic that you calculate there on the right. But with the mean, there's two different test statistics, one based on the t-distribution, the other based on the normal distribution. And the way we differentiate with that is the same way we differentiated when constructing confidence intervals. The key question is, do we know what the population standard deviation sigma is? If we do know what it is, we want to use a normal distribution and calculate a z-score according to the formula you see there on the table. If not, then we want to use a t-distribution using, again, that similar equation adjusted for the t-distribution. Once we calculate the test statistic, okay, then we're ready to finish out our hypothesis test with a final comparison. But in all cases, no matter what test statistic we're using, we're working under the assumption that the null hypothesis is true. So let's apply this test statistic calculation to our gender selection example. Remember that we have this XORT method of gender selection which claims that you can increase the likelihood of having a baby girl. And we have a sample of 100 births. Of those 100 births, 58 are girls, which means 42 are boys. So we're dealing with proportion. So from the chart on the previous slide, the test statistic for proportion is this little monstrosity you see here for calculating a z-score. Now, in this equation, p hat is what we've always known it to be. It's the sample proportion. For our gender selection example, that's going to be 58 out of 100. 58 girls out of 100 births. That gives us 58%. P is the probability of success. So the probability of having a girl born is 50%. Q is the probability of failure, which, as you may recall from Chapter 7, is the complement of P. So we just take 100%, subtract out from the 100% the 50%, which is P, and that gives us Q, also 50%. Now we're ready to calculate our test statistic. So here's our test statistic. We substitute in what we know. So p hat 58%, P is 50%, and then on the bottom, underneath that radical sign, we've got P equals 50%, Q equals 50%, and N, which is our sample size, 100 births. Punch this out on your calculator, and out pops out 1.60. This then, Z equals 1.60 is our test statistic. Now we've got our test statistic calculated, we're ready to make the comparison we need to conclude our hypothesis testing and get our result. Basically what we're going to do is decide between those two conclusions that we can make. Either we reject the null hypothesis or we fail to reject the null hypothesis. And it all depends on where our test statistic stands in relationship with the critical region. Now there's two ways that we can go about making the comparison. We can use either a critical value or a p-value, one or the other. Typically I like to use both sometimes. You really only need to use one. It doesn't matter which one because either way you're going to come out to the same result. But I like to use both sometimes because then it's a cross-check to make sure that I'm not doing anything wrong with the way I'm conducting the hypothesis test. It's just a nice little convenience to have. I don't do it all the time, but every once in a while, when I doubt myself or doubt the result that I'm getting, then I'll go ahead and just do it the other way just to make sure that I didn't do anything wrong. Now, regardless of whichever standard we're using, whether we're using the critical value or the p-value, okay, we're going to have to know what type of test are we running, okay? We can be running a left-tailed test, a right-tailed test, or a two-tailed test. And depending on which one we're running is going to determine the size of the critical region and the critical value that we get out. So it's really important that we know what type of test that we're running. A left-tailed hypothesis test will have a critical region on the left side of the distribution. So here up at the top, towards the top of the screen, you see an example of a left-tailed hypothesis test. There's one tail critical region on the left side of the distribution. In this case, the alternative hypothesis will use the less than symbol when you write it out. A right-tailed hypothesis test will have a critical region on the right side of the distribution. So just underneath the left-tailed distribution, we have an example of a right-tailed test distribution because the critical region is on the right. A right-tailed hypothesis test will have an alternative hypothesis that uses the greater than symbol. Notice how in each of these cases, the inequality is like an arrowhead pointing toward the side of the distribution where the one-tail critical region resides. Of course, there's a third option. We could have a two-tailed hypothesis test where we have a critical region on both sides of our distribution. This is equivalent to what we saw earlier when we were calculating critical values of Z alpha over 2 or T alpha over 2, where we take that alpha and we split it into two parts and put one half on the left and one half on the right side of our distribution. This is the two-tailed hypothesis. Accordingly, this is going to occur when your alternative hypothesis is using a not equal to sign. And typically, the two-tailed test is symbolized by a claim that says the population parameter we're testing is equal to a certain value. We can't actually say that the alternative is equal to that claimed value for an alternative hypothesis, because by definition, that is what the null hypothesis is. The null hypothesis, by definition, says that the population parameter we're testing is equal to the claimed value. So when that is the claim itself, the way we reflect that in the alternative hypothesis is to say that the population parameter is not equal to, and this results in what's called a two-tailed hypothesis test. You see an example there on the far right of a two-tailed hypothesis test distribution. So there's two ways that we can make the comparison. One way is by using p-values. We haven't discussed p-values before, so let's talk a little bit about what a p-value is. A p-value, which is really just a shortened way of saying probability value, is nothing more than the probability that your test statistic is at least as extreme as the one representing the sample data. Again, assuming the null hypothesis is true. That's not a fancy statistics talk. What does that really mean in practical reality? Well, the p-value is a probability. And we know from our work in previous chapters that probabilities are represented by the area under the density curve. The specific area that we're looking at here for the p-value is the area of the tail in our distribution that's bounded by the test statistic. So for a left-tailed hypothesis test, the p-value is the area under the curve to the left of the test statistic. For a right-tailed hypothesis test, the p-value is the area to the right of the test statistic. For a two-tailed test, that area is split one half on the left, one half on the right. So the p-value is then going to be twice the area of either one of those tails. It's the area under both tails that combines to form the p-value. So when you're actually calculating p-values for a two-tailed test, oftentimes, especially if you're using the z-tables or a calculator inside software, you're going to be looking at taking the value that you find and then doubling that to get the p-value for a two-tailed test. Now, we're going to reject the null hypothesis if the p-value is less than our significance level. So what we're comparing is, once we get that p-value, which is the area under the curve, we're going to compare it with our significance level, which is the area of the critical region. So we're comparing two areas, essentially. If the p-value is less than the significance area, then we're said to be within the critical region, and therefore the p-value will lead to us rejecting the null hypothesis. If, on the other hand, the p-value is greater than the significance level, that means our area is bigger than the area of the critical region. We can't fit the area of our p-value into the critical region because it's bigger. Therefore, we're said to be outside the critical region, and therefore we fail to reject the null hypothesis. Alternatively, instead of using p-values, we could use critical values to run our hypothesis test. So, as we know, the critical value is the boundary of the critical region in our distribution. So there's a tail that we're calling the critical region, and the boundary between the tail and the rest of the distribution is the critical value. Remember, okay, our significance level alpha determines the size and hence the boundary of the critical region. So the larger alpha is, the closer that critical value is going to be to the mean value of our distribution. Whereas the smaller significance level we have, the smaller alpha is, then the further away from the mean value our critical value will be. What this means for hypothesis testing is that if our test statistic is found to be inside the critical region, then we're going to reject H0. However, if the test statistic is outside the critical region, we're going to fail to reject H0. So, if we're in the tails, then we're going to reject the null hypothesis. If we're not in the tails, then we're going to fail to reject the null hypothesis. Let's apply this comparison procedure to our gender selection example. From our alternative hypothesis, and here we have our alternative hypothesis repeated in case you forgot what it was. So H1 is P is greater than 0.5. So from this alternative hypothesis, we know we have a right-tailed test because our alternative hypothesis is using the greater than symbol. So notice how it's pointing to the right. So our tail is one tail on the right of our distribution. We can use our p-value to complete the hypothesis test. First, we have to calculate it. So the way we do that is looking at our test statistic, 1.6. Okay? Remember, the p-value is the area underneath the curve that's bounded by the test statistic. So I'm going to put my test statistic into this normal calculator and then punch out the area under the curve comes out to be 0.0548. If I'm rounding to 4 decimal places. I'm then going to compare my p-value with the significance level. And we weren't really given a significance level, so let's just say we use the most common, the one that's commonly picked by far, 5%. So 0.548, which is our p-value area, is greater than 0.05, which is our significance level. Therefore, we are outside the critical region, and we can fail to reject the null hypothesis. A way to think about this, if you're using p-values, is to think about this is an area under the curve. So there's a certain area bounded by the test statistic. It's a certain size. We're going to compare that with the size of the area under the curve made by the critical region. In this example, the p-value area is greater than the critical region area. That means we can't fit the p-value area into the critical region area because it's too big. It can't fit in. And because it can't fit in, we're said to be outside the critical region. Therefore, we fail to reject the null hypothesis. Now, alternatively, we don't have to use p-values. We can use the critical value to complete our hypothesis testing. First, we need to calculate our critical value. So with a 5% significance level, we know that our z sub alpha, or z sub 0.05, is 1.645. You can calculate that, look at the table, or if you've run into that number so many times you have it memorized, you just bring it out. There it is, 1.645. Now we're going to compare our test statistic with our critical value. 1.6 is our test statistic. It is less than 1.645. We're conducting a right-tailed test. That means our test statistic is outside the critical region, and therefore we fail to reject the null hypothesis. To look at that in a graphical format, we have a critical region bounded by the critical value that we calculated earlier. If we are inside that critical region, we reject the null hypothesis. If we are outside the critical region, we fail to reject the null hypothesis. Our test statistic places us just to the left of the critical value. That means we are outside the critical region. Therefore, we fail to reject the null hypothesis. Notice that regardless of whether you use p-values or you use critical values, you're going to come to the same conclusion. Like I said previously, sometimes I like to use both methods just to double check myself to make sure I did this right. So, to recap how we make our decision with our hypothesis testing, if we're using a p-value, you want to compare the p-value with your significance level alpha. You will reject the null hypothesis if the p-value is less than or equal to the significance level. If the p-value is greater than the significance level, then you fail to reject the null hypothesis. If, on the other hand, you're using the critical value to determine your decision on the hypothesis test, you want to compare your test statistic with your critical value. If your test statistic is inside the critical region, reject the null hypothesis. If it's outside the critical region, you fail to reject the null hypothesis. Either way you look at this, you have the same basic concept, whether you're going to compare areas or horizontal axis values. You reject the null hypothesis when you're inside the critical region. You fail to reject the null hypothesis when you're outside the critical region. So if you reject when you're in, you fail to reject when you're out. Now, we can't very well state our conclusion in that way because that's statistical lingo. Those who aren't up with the statistics, they don't understand the math behind it. That's why they hired you, so that they didn't have to understand the math. You could just give them the result. They need to understand the conclusion in a way that's actionable. So we need to know how to phrase the conclusions that we make from our hypothesis test. The proper wording is a little different depending upon your situation, and what it's really going to depend on is whether you have a one-tail or a two-tail test, and whether you reject or fail to reject the null hypothesis. If you reject H0 in a one-tailed test, the way to state your conclusion is there is sufficient evidence to warrant the claim that yada yada yada. If, on the other hand, you fail to reject H0 in a one-tailed test, left-tailed or right-tailed, the way you phrase your conclusion is, there is not sufficient evidence to warrant the claim that yada, yada, yada. If you reject H0 in a two-tailed test, you can say the sample data support the claim that yada, yada, yada. Because remember, rejecting the null hypothesis is the logical equivalent of accepting the alternative, and the claim is reflected in the alternative hypothesis. So rejecting the null hypothesis is a logical equivalent of accepting the claim. However, on the other hand, if you fail to reject the null hypothesis in a two-tailed test, you should say there is not sufficient sample evidence to support the claim that yada, yada, yada. So here's how that would play out for our gender selection example. We failed to reject the null hypothesis in a one-tailed test. So we state our conclusion in this way. There is not sufficient evidence to warrant the claim that with the XORT method, the proportion of girls is greater than the 50% that occurs without treatment. This is the way you should phrase your conclusion. Now, some things to consider now that we've gone through the basic steps of hypothesis testing. As we just stated with talking about how to state your conclusion, you never want to end with saying that you reject the null hypothesis or you fail to reject the null hypothesis, because that's statistical lingo. Most people won't understand it. And a lot of the people that are in management, they probably never took statistics. Again, that's why they hired you, because you know how to do it. So they don't have to learn. They just let you do the work, and then you give them the result. But you need to give them the result in a way that's actionable. And it's not going to be actionable if they don't understand what it is that's going on. So you've got to be able to word your conclusion in a way that non-technical people can understand and act on the result. Another thing to keep in mind is that there are some statistics textbooks and some online resources that use phrases like accept the null hypothesis. And one of the main reasons why this is done is because there are some educators who believe that this type of phrasing will help the students understand better. Instead of saying reject the null hypothesis and fail to reject the null hypothesis, they actually teach accept the null hypothesis and reject the null hypothesis as the two options for what you can conclude. This really isn't correct. And while it may help them to get through a particular homework assignment or a test, it doesn't really convey the full concept of what we're trying to do with the hypothesis test. In the first place, if we were to accept this premise that we're saying, okay, we accept the null hypothesis, well, that implies that we're trying to prove the null hypothesis. But it's not the null hypothesis that we're trying to prove. It's the claim that's being made that we're testing. That's what we're trying to prove. And the claim is not reflected in the null hypothesis. The claim is reflected in the alternative hypothesis. So there's really no accept the null hypothesis because there's no proving the null hypothesis. There's no real test of the null hypothesis. It's part of the test, yes, but it's not what we're really testing. What we're really testing is the claim, and that's reflected in the alternative hypothesis. To say fail to reject the null hypothesis is much more correct and accurate because it provides this nuance of meaning that says we might not have all the evidence that we need to reject the null hypothesis, which is the logical equivalent of accepting the alternative hypothesis or accepting the claim that's reflected in the alternative hypothesis. So we really need to be mindful of the language that we use and want to say fail to reject the null hypothesis and not accept the null hypothesis, because there is no accepting the null hypothesis. What What we're doing is testing the claim reflected in the alternative. So the null hypothesis is just flip-flop from that. This brings us to type 1 and type 2 errors, which we mentioned earlier in the lecture, and I said we would get back to, and now it's time for us to get back to it. This is not the first time we've actually encountered type 1 and type 2 errors. We encountered this before previously when we were talking about probability. We encountered it again when we were looking at confidence intervals, and now we have it here again. We're talking about hypothesis testing. This shouldn't be a surprise, because if the alpha is the same for confidence intervals and hypothesis testing, then that means that we're going to see type 1 and type 2 errors in both scenarios. Now, when applied to hypothesis testing, we can look at two actual scenarios. Okay, the null hypothesis will actually be true, or it will actually be false. It's one or the other. And in either scenario, we're going to reach one of two conclusions. We're going to reject the null hypothesis, or we're going to fail to reject the null hypothesis. If the null hypothesis, H0, is actually true, what we want to do is fail to reject it. We don't want to reject something that's actually true, so we want to say fail to reject the null hypothesis. That's a good conclusion when H0 is actually true. However, if we do reject H0 when it's actually true, we commit what's called a type 1 error. The probability of a type 1 error is alpha. So this is our significance level that we selected for our hypothesis test. This is the probability that we're going to reject H0 when H0 is actually true. Conversely, if H0 is actually false, we want to reject it. If it's false, we want to reject it. That leads us to a good conclusion. However, if H0 is actually false and we fail to reject the null hypothesis, we commit what's called a type 2 error, failing to reject a false H0. The probability of a type 2 error is characterized by the Greek letter beta. So we have alpha symbolizing the probability of a type 1 error, beta symbolizing the probability of a type 2 error. Now, here's how this applies to our gender selection example. So type 1 error would be concluding the probability of girls is greater than 50% when in fact it isn't. Something that's very helpful when trying to determine what a particular type 1 or type 2 error would be for a particular situation is to go back and look at your null and alternative hypotheses, because that's exactly what this whole chart is about. So here we have our null and alternative hypotheses listed here. Population proportion is 50%. Population proportion is greater than 50%. Remember, a type 1 error means we're rejecting the null hypothesis when it's actually true. So in this case, we're rejecting null hypothesis, p equals 0.50, when in fact it is true. That means we're concluding the probability of girls is greater, because remember, rejecting the null hypothesis means accepting the alternative. So we're going to say the population is greater than 50% when actually it is equal to 50%. Conversely, a type 2 error, okay, is where H0 is actually false, but we fail to reject it. So this would be the same thing as concluding for this particular example that there isn't sufficient evidence to say the probability of having girls is greater than 50% when in fact it is. In either case, we're going to need to go back and get some better data. Now, better data could mean more data. Better data could mean more representative data. Data that's actually what we many industries call quote unquote clean data as opposed to dirty data. Very often in real life scenarios, better data means both. You need more data and you need higher quality data. Either way, you want to be sure to minimize your type 1 and type 2 errors. Well, how do we go about doing that? Well, suppose we have a fixed sample size n. If we decrease alpha, we're going to increase beta. Here's a graphical illustration that should be able to help with that. So if we're fixing the sample size n, that means the shape of these curves representing the null hypothesis and the alternative hypothesis is fixed. Then what we're doing is we're looking at this region of overlap. So there's a region that's overlapping both. To the right of, in this case, we're looking at a mean. This could be a proportion, what have you. It's some critical value. So the area to the right of that critical value is going to be alpha, which is our type 1 error. However, the area under the alternative hypothesis curve to the other side of that critical value is our type 2 error, which is beta. So if we're going to decrease alpha, and we decrease alpha, that's going to take this critical value and shift it over to the right so that this area under the curve in red becomes smaller. What's that going to do with this area in this teal color, which is beta? It's going to increase it. It's going to make it go bigger. So if we fix the sample size and we decrease alpha, that means we're going to get an increase in beta. It's going to become more likely to make that type 2 error. On the flip side of the coin, still keeping that sample size fixed, if we increase alpha, which means that critical value is going to move to the left so that this area gets bigger, that means the area here under this curve, beta, is going to get smaller. So we can increase one, decrease the other, decrease one, increase the other. It's a trade-off when our sample size is fixed. Let's say now that we're not going to fix the sample size. We're going to make that variable. We're going to instead fix alpha. How does that play into the value of what beta is? Well, if we increase the sample size, that's going to change the shape of these two curves. And the way the shape is going to change is that the curves on top are going to go up. So the curves are going to get taller, and they're going to be less wide. They're going to be much more narrow. So they get taller and narrower. Well, what is that going to do with these areas here under the curve? If we fix alpha, then this critical value is in a fixed position. And if you squeeze this, so you stretch it up, so then that's going to bring the line in, shift it toward the right, and that's going to cause a decrease in beta because this line is just going to go more narrow. So this whole thing is going to come, it's going to squash this area. It's going to come down. That's going to be a decrease in our type 2 error, which is beta. On the flip side of the coin, if we fix beta and we increase the sample size, then that's going to cause a decrease in alpha. So naturally, what we want to do is decrease both type 1 and type 2 errors. The way to do that then is to increase the sample size. What this means is more data is always better than less data. You always want to try to get as much data as you can. In the real world, where you're having to deal with limitations of resources, and you're also dealing with limitations of data collection, so oftentimes you're missing data, oftentimes some of the data you have is poor quality, often you have both. You really just want to get all the data that you can. So even though we run calculations for minimum sample size, and it's very often in the real world, you're going to want to exceed that. You're going to get as much above that minimum sample size as you can because more data is good data. And more data just makes for a better analysis because it limits or reduces the probability that you're going to commit a type 1 or a type 2 error with your hypothesis test. This leads us into the concept of the power of a hypothesis test. We're really not going to do much with this concept, but what you need to understand is that the power of a hypothesis test is the probability of 1 minus beta. Okay, so in essence, we have our overlapping curves. Notice how these curves are less wide, so they're narrower, and they're also taller. So that's the effect of increasing sample size. So you can see that this region down here where they overlap gets smaller and smaller. So beta is this area to the left here of your critical value. So the area then to the right is going to be 1 minus beta. Now, this value depends on the significance level alpha as well as the population parameter that you're testing with your hypothesis test. And it's essentially used when you're trying to consider sample size while designing an experiment. Design of experiments is actually just beyond the scope of this course, which is why I say we're not going to do a whole lot with power of a hypothesis test, but it is good to know that it's equal to the probability 1 minus beta. Now, just as 5% is a common choice for alpha, 80% is a common choice for the power of a hypothesis test, this 1 minus beta. That means that we're saying that beta is going to be a maximum of 20%. There are statisticians that argue for a higher power of a hypothesis test, 85%, 90%, but the most common convention, and that's what this is, it's a convention, the most common convention is to use 80% for your power of hypothesis test. So when designing an experiment, having this goal of at least 80% for your power of hypothesis test becomes important when you're determining the minimum required sample size. And that brings us to the end of this lecture. If you have any questions, you know how to get a hold of me. Otherwise, I will see you in class. Thanks for watching.